Hi, I'm Rishabh More, PhD student in the School of Mechanical Engineering at Purdue University, and this presentation I'll be talking about the effect, the influence, how the microscopic roughness influences the bulk rheological properties of dense suspensions. So, about a couple of decades ago, particles were considered to be perfectly smooth for all the numerical and theoretical purposes. But if we look at the uh, AFM images of the surfaces for these particles, you can see there are these small bumps on their surfaces, which means the particles are not perfectly smooth. So the immediate consequence of this roughness is can be seen in the interaction of two spheres in a Stokes flow. So this roughness leads to asymmetry in the trajectories of two particles. So that means since the roughness is influencing the pair interactions, it would have some non-intuitive effects on the bulk properties of the suspension. So uh, we can think that if by increasing roughness, the the width of the lubrication film would increase between the particles, and that would actually lead to reduction in hydrodynamic stresses, and as a consequence the viscosity should decrease. But that is not the case in dense suspensions, as it has been shown by Tanner and Dye. In these experiments, they artificially roughened the particle using a grinding process, and what they found that increasing the particle roughness actually increases the suspension viscosity. So to address uh, why this happens, we can think about roughness and its consequences on on the particle. So if we have roughness, then we expect the particles to come into contact, and contact between the particle lead to contact forces, especially friction. And and, and since friction is dependent on the roughness size, we we expect uh, we expect that roughness would influence the rheology. So we so to answer why increasing roughness increases the suspension rheology, we basically model the hydrodynamic interactions using the Ball-Melrose approximation, and we model the roughness as a hemispherical bump on the particle surface, and we split the normal forces into we split the contact forces into a normal force and a tangential force, and we also incorporate friction, and and by calculating the stress in the system, we can also measure all the rheological properties such as shear stress, relative viscosity, and normal stress differences. So for the friction, we use this normal load dependent coefficient of friction, which decreases with normal load, because this it has been observed that by using this friction law, we can recover the shear thinning that is observed for suspensions with intermediate volume fractions. So yeah, so if it is well known that with increasing friction, the viscosity increases. So so if high roughness leads to a higher friction, then that means that would increase the suspension viscosity, and that is what we exactly observe. So this plot shows the average coefficient of friction between all the particles. As we as we increase the roughness, you can see the friction between the particles also increases, and because of this, the viscosity of the particles also increases, as shown in this left plot. And again, we split the stress contribution into hydrodynamic and a contact and the stress that is coming from contact interactions. And as we increase the roughness, the hydrodynamic contribution is decreasing, but the increase in the contact contribution uh, is uh, is basically overcompensating this decrease, and as a result, the viscosity is increasing. Uh, Another consequence of increasing roughness is that the jamming fraction at which the suspension stops flowing, it also decreases, as tabulated in this plot. So what will happen if we increase the roughness of particles in a dense suspension setting? So since increasing roughness decreases the jamming fraction, we expect the suspension to basically undergo shear thinning at an earlier shear rate, as well as uh, at a earlier at a low value for volume fraction. And again, this was observed in these nice experiments where the roughness was introduced artificially by attaching these nano particles on the surface of the base particle, and they basically observed that increasing the roughness leads to earlier shear thinning and as well as a switch in the sign of the first normal stress difference. The same observations were made in another paper uh, again here. So for this, we basically we use a critical load model because it is used commonly in the literature to recover the shear thickening behavior in suspensions. So the idea is basically that the friction force will be zero if the normal force between the particles is lower than a threshold value, which is denoted by FCL, and the friction will be activated once this normal load becomes larger than the critical larger than the threshold value. So what we observe that increasing the roughness uh, leads to a stronger shear thickening jump, and at low volume fractions it basically increases the magnitude of the shear thickening effect, but at higher volume fractions, as we increase the roughness, it makes the suspensions to undergo uh, discontinuous shear thickening. That means the viscosity jumps abruptly at a given at a critical shear rate. And again, with increasing roughness, we see that the critical shear rate required for the shear thickening transition decreases. And also, increasing roughness decreases the critical volume fraction above which we observe discontinuous shear thickening. So for 1% roughness, we see that the critical volume fraction for DST is around 57%, but for a 5% roughness, it is significantly lower, and the suspension undergoes discontinuous shear thickening at only 53%. We also observe the we also observe that the first normal stress difference basically switches sign after the shear thickening transition, as it was observed in experiment, and the second normal stress is negative, and it follows the same behavior as the stress in the system. Yeah, so to answer why roughness leads to earlier onset of shear thickening, we look at the contact networks, which are plotted for two different roughness values, one low and one higher. So the lines here indicate the contacts between the particles, and the dots at the end of the lines are the particle centers, and this color bar represents the magnitude of the normal force between the particles. So as you can see, the the density of the contact networks increases drastically if we increase the roughness, uh, and also the magnitude of the normal force between the particles increases, and because of that there is a very high contact stress in the system at higher roughnesses, and because of that we basically get a stronger jump in the viscosity as well as a discontinuous shear thickening at lower volume fraction at higher roughness. And finally, we to basically quantify the effects of roughness, uh, we come up with this constitutive model. So as you can see, the rheological properties in the lower and a very high shear stress limit are basically independent of the stress values. So we can model them uh, as a function of roughness and only the volume fraction in both these limits, which are indicated by 0 and this infinity superscript. And for the intermediate stress values, we can basically interpolate between these two extremes uh, to to predict the values of these properties in the intermediate stress region. So to do this interpolation, we use this function f, which is basically the fraction of frictional contact at a given stress sigma. And if by plotting this fraction for all the simulation data, we observe that this lies on a single curve, and this is what we use for interpolation. Yeah, so this slide shows the fitting constants uh, versus the roughness. So the fitting constants for viscosity and the second normal stress difference decrease as we increase the roughness. Similarly, jamming fraction also decreases as we increase the roughness. But since we see this switching in the sign of first normal stress difference, the the fitting constant for the first normal stress difference actually increases, and it also switches sign as we increase the roughness. And yeah, finally this plot shows the uh, fit in the low and basically high shear rate limits for the viscosity. Yeah, and if yeah, so here we basically show the effectiveness of the constitutive model by plotting the simulation data with along with the model. And one more thing to mention here is that if you look at this stress versus shear rate state diagram, we observe basically three different curves. One is this monotonically increasing, the other one is this S-shaped curve, which uh, indicates basically the onset of discontinuous shear thickening, and the third one is this backward bending curve, which happens for volume fractions very close to the jamming fraction. Next is the model is also very effective in capturing and quantifying the second normal stress difference, and it also captures the switching in the sign of the first normal stress difference as shown in this plot. Yeah, so to summarize everything, uh, we, we we have this phase diagram for shear stress versus volume fraction, and as we increase the roughness, this shows the various regions where basically we have monotonically increasing curve, then the S-shaped curve and the backward bending curve. And as we basically increase the roughness, the DST the transition from CST to DST takes place at a lower volume fraction. Yeah, that's it. Thank you.